Okay, I think we'll get started. So today we're going to talk about concentration and particularly molarity, it's a type of concentration. We'll also talk about pH and the pH scale because that's related to concentration. So there are a number of common concentrations that are used throughout chemistry. In general chemistry, we most often deal with molarity, and this is moles of solute, moles of the thing that we're interested in, per liter of solution. A liter of the solution. Now it turns out that actually gets hard to work with in a couple of cases. One, when there isn't a real distinction between the solute and the solvent. So if we're mixing, say, alcohol and water, we want to go from almost all alcohol to all water, for example, then molarity isn't often the best. Further, for direct comparison, actually, in some of experiments, and we run into this in the lab all the time, and that is when you mix things from a solution, they don't always, the volumes don't necessarily add. So if you take 1 milliliter of solvent A and mix it with 1 milliliter of solvent B, and you mix them, you don't get necessarily 2 milliliters as you would expect. And you can kind of think about this as, let's say you had a truckload of basketballs and a truckload of ping pong balls. If you mix the two, the ping pong balls will kind of find the cracks in the larger basketballs, and you'll actually get less than 2 truckloads. And the opposite can happen as well. So let's say you had a truckload of books and a truckload of basketballs. If you mix those, well, the books and the basketballs can't stack as well as when they're alone. So you get more than 2 truckloads worth of volume. So with all that said, it turns out working with something called molality, which is moles of solute versus kilograms of solvent, is often easier to do because you can weigh out very easily the amount of solute you have, turn that into moles with the molecular weight. That's all direct and clear, and then you can weigh out the solvent that you're putting in rather than measuring out with the volume. Weight percent, kilogram solute versus kilogram of solution. This is often used in certain specialized areas where everything is repeated. So you might see this in agriculture and certain amount of weight percent of this particular fertilizer. Lots of places like that. Then finally, mole fraction, and this is ideal for the case when there isn't a clear solute or solvent. So I really shouldn't even say moles of solute. We should really just say moles of A over total moles, and that would be the mole fraction. The symbols here are capital M, lowercase m, usually a W and a %, and then here is X, and then let's say that is a subscript with whatever mole fraction you're talking about. So those are the typical symbols. For molarity, we'll often use this. So we would say something like this. We'll use a square bracket to indicate concentration. So this would say the concentration of sodium chloride solution is 0.12 molar. We'll often write something like that. So the square brackets indicating concentration when we're talking about the substance, and then a capital M is the unit on the number. All right, let's just work through a few examples. So let's say we prepare a solution where we put 30 grams of sodium chloride into a volumetric flask that's 500 mils, and so we fill up with the water, enough water to reach 500 mils. Now note, we haven't put 500 milliliters of water in. We've filled up so that the total solution is 500 milliliters. Now, well, we can write 30 grams in the half a liter of solution now. So we could put solution here. Often we don't put anything. So you wouldn't put sodium chloride, you wouldn't put water. You would just put solution if you want to put something, or just leave it blank. And then, so this is what we've prepared. So basically you can think about, what did I put in the flask? And then we simply do a grams to moles conversion. And that's a very quick calculation to get us to a 1.027 molar solution if we were to make this up. Let's say we want to know the grams of NaCl that are in 250 milliliters of a 0.15 molar solution. So what this would be, physically, if we took 250 mils of this solution and then we let it evaporate all the way down so all the water was gone, how many grams of sodium chloride would there be? And so here we can take our 250 milliliters, now in the form of liters. We know the molarity, that's from over here. So as a unit, capital M is representing moles over liters. So here's writing this out to help us with our unit analysis. Then we can do a moles to grams conversion, and we get the grams of sodium chloride in this for this problem. All right, let's do a dilution problem. So let's say we add 1 liter of pure water to 100 milliliters, 0.1 liters, to 0.5 liters of 0.2 molar NaCl. So we can see here we're doing a dilution. We're taking a volume of a prepared solution, 0.2 molar sodium chloride, and we are adding pure water. We're diluting the concentration. So we expect that we should get a value less than 0.2. Okay, well, let's do it systematically, and then we'll do it in the shortcut method. So systematically, the first step is to figure out how many moles of sodium chloride are coming to the party here. So we're putting 500 mils of this sodium chloride solution, and then pure water, which brings no moles of sodium chloride. So the moles of sodium chloride are coming from simply the original half a liter. Now, where do they go? They go into this new volume, 600 mils, because that's the solution plus the pure water. So there's our total 600 milliliters. So now we know we still have only this many moles, right? The water didn't add anymore. And so we can work out the molarity and we get this. Okay. Now, there's a shortcut that's very handy in the laboratory, and that is M1V1 equals M2V2. And so we know everything except the new molarity. And so we can quickly do that calculation, and we get the same value. Now, I want to caution you here, this only works for dilution problems. So perhaps you can challenge yourself and say, instead of 0.1 liters of pure water, we added 0.1 liters of, say, 0.3 molar sodium chloride. So definitely not a dilution problem anymore. Then this won't work, and you just have to track where are those moles coming from, and then what's the new volume. All right, so that's concentration, and we'll be using molarity as our primary unit of concentration here throughout this course. We'll see mole fraction and other things a little bit, but mostly molarity. Your book will have a lot of problems on this, so good to work those out. Now, just to finish here for a bit, let's talk about the concentration of H+, and that gives rise to something called the pH, which you're probably familiar with, at least a little bit. If we look at water actually auto-dissociates, and it does to a very small degree. So most of the water in a glass of water is H2O, but a very small amount, 10 to the minus 7 molar, is H+, and thereby exactly 10 to the minus 7 molar is OH minus. So there's this, water breaks up. And this actually sets the pH scale, and it sets the neutral. So if we take pH, now the operator little p means take the negative log. So we'll run into pH, POH, pK pKa, pKsp. So there's, whenever we see this little p, it simply means take the negative log of whatever the concentration or whatever number it's next to. So pH is just minus log of the H plus concentration. For pure water, that would be minus the log of 1 times 10 to the minus 7, which is 7. So neutral water is a pH of 7. Anything less than 7 is considered acidic. That's an acidic solution, means we're less than pH 7. And if we are greater than pH 7, we're basic. Now, let's do just a quick calculation. Let's say we have the pH of, we want to know the pH of this solution, 0.00125 molarity HCl solution. Well, this is going to break up completely. This is a strong acid, so we will create this will be our H plus concentration. So this will be our concentration of H plus. And we put that in the log and we get 2.9, and we might expect that this should be an acidic solution. Now, the auto-dissociation number 7 actually sets the pH scale. So, in some sense, there isn't any meaning to a pH less than 0 or greater than 14. You can put some chemical sense to it in terms of what's a stronger acid versus a less strong acid, but that's putting some extra chemistry on top. The solvent and its auto-dissociation sets its own pH scale. And so for water, because this is 7, what we do, and we'll see this a little more later, is we can go from 0 to 7, and then to 7 plus 7, so 0 to 14. If we had another solvent, like methanol or something, that has a very different auto-dissociation, and that will have a different pH range. Now, we don't worry about running into those organic chemists who do organic chemistry in non-aqueous solvents do need to worry about that. But we need to worry about water. Okay, so we have a pH scale of 0 to 14. Now, what is that 0 to 14? It's the pH plus the pOH. And this, again, I'm just saying this now, but we'll be able to understand that as we get more and more through chemical equilibrium and equilibrium constants, which are coming up very soon. Okay, so let's figure out the pH of a same concentration, but a sodium hydroxide solution. So here, sodium hydroxide is a strong electrolyte. It's a strong base, so it will break up and increase the amount of OH concentration. So we expect we better get a basic solution. Well, so how we do this is we first calculate the pOH, which is done the same way as we did the pH up there. So we get the same number, 2.9. And then pH is just 14 minus pOH, which is coming from this. And we get 11.1, which makes sense because it's a basic solution. All right, well, let me do another one. Very similar problem here. Let's calculate the pH of a 1.25 times 10 to the minus, I want to do 8 here, not 9. 10 to the minus 8 molar solution of HCl. Well, this is a strong acid, so all of that will break up to form H plus. And so we'll plug that into the minus log. And when we do that, our calculator will give us, rightly so, 7.9. But that's basic. So how can we add acid to a solution and get a basic value? Well, what we failed to take into account here is that we have so little, we've put so little HCl that it's small compared to the auto-dissociation of water itself. So pure water is more of an acid solution than this 10 to the minus 8th HCl. And so if we look at the total concentration of H+, we get 1 times 10 to the minus 7 from the water and 1.25 times 10 to the minus 8 from the HCl. So that gives us a 1.125 times 10 to the minus 7 concentration. We have to add those two. And when we add those two, we get 1.125 times 10 to the minus 7 minus log of that is 6.95, so it is acidic. So the moral of the story here is these calculations seem trivial, but you have to know what's going on and where this all comes from. So yes, this is totally correct, what we did here. And it will be until we get down to concentrations that are close to that of water. So if we're getting down to 10 to the minus 5, we're probably still okay. 10 to the minus 6, then we have to worry about adding in the 1 times 10 to the minus 7 for the water. Certainly if we get to minus 7, minus 8, minus 9, minus 10, anything below water, then we have to just use water. If we get to like 1 times 10 to the minus 10 or 10 to the minus 12, then water dominates and we would just get a pH of 7. So we'll cap out at a pH of 7 there. Okay. Right. And the same would be true if we were looking at a sodium hydroxide solution. We would get a POH that would, when we plugged it into this, give us a acidic solution for the very same reason. We would have to add water if we start to get concentrations close to that of water. So good to know how to do these calculations, but really understand the chemistry that's behind this and giving rise to this pH scale.